let's get started. And any question from last time? So let's go over a bit of a review from last time because we covered a lot last time. So I think last time we go over, or we should go back a lot. Okay. So we go over those 8 properties of the ROC. Okay. So we see that very big difference between Laplace transform and the Fourier transform is we need to be careful about its region of convergence. This ROC, and we talk about this A property of ROC. And the first property is probably one of the most important ones. Is that, and actually 2 properties here in this one property. And so first property says that ROC consists of strips of vertical lines in the S-plane, so basically strips parallel to j omega axis. And later we see that there can be almost one strip in the in the ROC. So there is either one strip either extend to left, extend to right, or everything, but there cannot, or there is nothing, but there cannot be 2 strips. Okay. And there is also this property 1.1 that we think is true, which we have a shaky derivation. Says that something is ROC if only if the the corresponding Fourier transform is convergent, and the corresponding Fourier transform is saying that this strip at the point sigma, and so we think that the Laplace transform on this line is like Fourier transform of x of t e to the minus sigma t, and we think this is convergent, and we we say this is if only if x of t e to the minus sigma t is absolutely integrable, so this integration has finite value. So we think that we think that the sigma line is in ROC if only if this integration is absolutely this integration is finite. Okay, so integration of minus infinity to plus infinity absolute value x of t e to the minus sigma t dt is one. This is be finite. Then this this vertical line at sigma is inside ROC. Okay, so that's property 1 and property 1.5. And then property 2 is the derivation is pretty obvious. It says that the ROC should not contain poles, and that's just because it poles the Laplace transform diverge. So it diverges, so it's not converging. Okay, and the next property says that. Okay, then the next 4 property is a set. It's a bit confusing, but let's just gloss it over. And it says that the ROC can actually have like 4 shapes, and they correspond to 4 different signals in your time domain. So we say if your signal is finite duration like this, it has a left boundary and a right boundary, then your ROC will be entire plane. Okay. And then the next one, which says that if your signal is right-sided, so you have a left boundary and on right side you can do whatever, then your ROC will be also right-sided, will extend to the right to infinity. And the next one is the other side, and they say your signal on time domain is left-sided, so extend to the left side to infinity, then your ROC will also extend to the left side to infinity. And finally, the next one, the first one says that if your signal is 2-sided, so it's just whatever signal, then your ROC is a strip. Okay, so yeah, your ROC will be like this one strip, or sometimes the ROC doesn't exist, as we see this example. So we see a 2-sided function is like a left-sided function plus a right-sided function, and you want the ROC to be intersection of both of them. And if they have an intersection, you have ROC. If they don't have an interaction, your signal just doesn't have a convergent Laplace transform anywhere. Okay, and finally we have these 2 interesting properties, 7 and 8. 7 says that if your Laplace transform is rational, then your ROC has a very nice form. It says it's always bounded by poles or infinity. Okay, so the ROC, so for example, so by this property, then you can just read your ROC. You can just classify all possible ROC of your rational Laplace transform if you know it's pole-zero plot. So for example, we have Laplace transform here, and we see it has 2 poles here. then because the ROC are strips bounded by the poles, so we can just look at the real coordinate of those poles and just read out ROC. We see that the ROC can be either this right-sided part or in the middle part or the left part. So because there are two poles, so there are these three ROC here. Okay, and finally on property 8, it says that this property 8 is a combination of property 7 and the previous ROC. And the property 3 to 6, it says that if you're a rational function, then then if your function is right-sided, then your ROC must be the rightmost ROC here. And if your function is left-sided, then your function ROC must be the leftmost one here. Okay. And yeah, so that's the properties of ROC. Okay. And then we talk about how to do inverse Laplace transform. And there are two ways. So one way is you can do this complicated integral, which if you think about a contour integral, you don't really know how to do. But you think about you integrating over this real omega line, we kind of know how to do. But a lot of time it will be really hard. Okay, so we skip. So we just write down this formula here and forget about it. And then we say the most of the inverse Laplace transform we'll do is we'll do it for the rational function. So I think if your big X of S, if it's a rational function, then we can always do this partial fraction expansion, break it into those how do I call it, partial fractions, and then we just look up the table and see what are the inverse Laplace transform of those partial fractions, and have our inverse Laplace transform. But we also see that this is harder than what we do than when we do this in chapter 4. It's because there is a ROC. Okay, and so each algebraic expression. So for example, this partial fraction here, you can have multiple possible inverse Laplace transform depending on which ROC you pick. So for example, in this example, is X of S equal to equal to S plus 1 minus S plus 2, and we see that it has 3 possible ROC you can pick, and for these 3 possible ROC you will have 3 different possible inverse Laplace transform corresponding to each partial fraction being picking the right-sided one or the left-sided one. Okay, and yeah, so I guess a good picture is we go back to here, and yeah, so these 3 different ROC will correspond to each pole. So each partial fraction will correspond to each pole, and yeah, so each ROC will correspond to whether you pick both the right-sided function for both poles, or one of them being right, one of them being left, or you pick both of them being left, and that will correspond to these 3 different ROC, 3 different functions here. Okay. And yeah, any question about the quick review of last time? Oh, I guess there is one more thing. So then we also talk about having the geometric evolution of Fourier transform from pole zero plot, and basically just says that if you have a rational function and it has a whole bunch of poles and a whole bunch of zeros, the pole and the zero basically tells you what your rational function looks like. And so when you mark the point 0 on your on your plane, and then you can kind of read how your Fourier transform change when you change omega, because Fourier transform is just a Laplace transform on this geometric axis. So you just try to read how this rational function, how its magnitude and angle change when you move around this geometric axis by looking at how whether it's approaching some poles and zeros. So for example, this is a very simple function which just have a pole and minus 1/2, and you think about your omega moving from minus infinity to plus infinity. Then when you are very close to this pole, you are dividing by something small, and your amplitude will be larger. And then you can also look at the angle of this complex number j omega plus 1/2. And so the angle should be from pi over 2 to minus pi over 2. And also we have an example of an interesting system that's open system that has this nice symmetry between the pole and zero. So it has like a 1 pole here and a 1 0 here. Then you see that when you move your omega around the omega axis, the magnitude is always the same. And the angle will kind of change. Okay, and so this is a picture of how the magnitude and the angle change when you change omega from minus infinity to plus infinity. So the magnitude is always the same because you think about is this complex number divided by this complex number, and they always have the same magnitude if S is purely imaginary and A is real. And yeah, and it has angle like this. Okay, so that's a quick review. And let's go to the topic we want to talk about today. So that's just like all the Fourier transform done. Now we want to talk about property of Laplace transform. And because we are talking about Laplace transform, and so so once again we need to think about RLC. Okay. So not only we need to think about how the algebraic expression change, like they are in Fourier transform, also need to think about how RLC change when we are trying to apply these properties. Okay, and let's start from the very easy example, that is linearity. So we have some time domain signal, small x1 of t, Laplace transform to big x1 of s, and has RLC R1, big R1, and then another signal x2 of t go to Laplace transform to big x2 of s with RLC R2. And then by linearity, this is easy to derive. So by linearity, you can derive this by just having write down the Laplace transform equation and see the integration is linear. Okay, and so we have a small x1, a times small x1 plus b times small x2, Laplace transform to a big x1 plus b big x2. Okay, so this part is just like all the Fourier transforms. And but also we have a weird thing. So RLC we want it to be like basically the intersection between R1 and R2 because we want both of them to converge. But this is a bit tricky. So most of the time it's just R1 intersection R2. But sometimes the RLC can be bigger than R1 intersection R2. It's containing R1 intersection R2. That's because some poles can cancel when you do this linear combination. Okay, and we know just about the property 7 we talk about today. We know that RLC is always bounded by poles for rational functions. So when some poles cancels, your RLC can extend. Okay, so let's just see a very easy example. Okay, and a very easy example is that we have x of t equal to x1 of t minus x2 of t. And then we think about, then we write down the Laplace transform. Big x1 is 1 over s plus 1, and having RLC, real part of s bigger than 1, and x2 is 1 over s1, s plus 1, s plus 2, RLC being real part of s bigger than minus 1. Okay, so this thing has a pole at minus 1, and this thing has a pole at minus 1 and minus 2. Okay. And we see that those are the RLC that we expected rational function. So it's bounded by pole and infinity, and it's bounded by pole and infinity and the strip. Okay, and so we have those two big x, big x1, big x2, and by linearity the corresponding big x should be big x1 minus big x2. Okay. And the RLC should be intersection of those two, so RLC should contain this real part of s greater than minus 1. Okay? But when we see that when we do this subtraction, so s1, 1 over s1 minus 1, 1 over s plus 1 minus 1 over s plus 1 s plus 2, and we see that actually the pole and the minus 1 kind of cancel out when you do subtraction. Okay? So in other words, when you like multiply all these things, and we see that you get extra factor of s plus 1 here, and it just cancels out, and the big x of s is actually 1 over s plus 2. And so you see that you actually only have a pole at minus 2. It doesn't have a pole at minus 1 anymore because of this kind of pole 0 cancellation on this s plus 1 and this s plus 1. Okay, so this s plus 1 pole just disappears when you do the subtraction. And so you need to extend your RLC to x at minus 2. at s plus 2. So this s equal to minus 2. Okay. And yeah, so that's what we say, why we say the RC is containing intersection, because RC can be larger than the intersection of two RC when some poles got cancelled out. Okay. And yeah, so that's the linearity. The RC is the intersection of two parts, but it can be larger when your poles got cancelled. Okay. And the next one is time shifting. Okay, so now we are doing this without proof, and we just say result. But you can imagine that the proof is really similar to the Fourier transform one. So we have x of t transform to Fourier Laplace transform to big X of s, and then we do a time shift on small x, and so small x of t minus t0 will Laplace transform to e to the minus s of t0, big X of s. This is very similar to the Fourier transform one, where so Fourier transform you have this s equal j omega equal minus j omega t0. Okay. And then so this is shifting in time domain, and the RC here doesn't change, so this one is nice. Basically because this e to the minus s t0 will not change the pole zero structure. Okay, and okay. And so this is the easy one, and the next one is more complicated. So basically you try to do a frequency shift, okay, and so you shift your big X of s on your frequency domain by some s0, but then you see that because you want to shift everything by s0, then all the pole and the zero shift, so you also want to shift your RC by s0. And but RC you only care about real part, so RC becomes the RC plus the real part of S0. And when you do the shift by S0, then on the time domain you get h e to the S0 t vector. Okay. Okay, so the algebraic part, once again we skip the derivation, but let's look at the RC part change. And we just, well, the result is that the RC will change shifted by real part of S0, and we can look at this because we can derive this by looking at where does the pole and the zero shift to. Okay, so but I guess more importantly, where does the pole shift to? Okay, so the pole of x of s. So if it has a pole at s equal to a, and the x of s minus s0 will have a pole at s minus s0 equal to a. And so s minus s0 equal to a, and that will be s equal to a plus s0. Okay, so it has a pole at s0, and now it's a pole at s0 plus a. Sorry, the pole at a, and now it's a pole at a plus s0. Okay, so kind of yeah. So maybe it has try to draw some pole. Okay. So think about maybe it has a pole here, so some pole at A here, and the A pole will get shifted to some A plus S0 here. Okay, so you get A plus S0 here, and so shift on the real part is A plus real part of shift is by, so the real part shift is by the real part of S0 here. Okay, and yeah, so that's frequency shift or the S domain shift. I try to do a S domain shift because you shift all the point 0. You also need to shift your RC by this real part of S0. Okay, and yeah, and shift. Then we can kind of go back to the Fourier transform thing. So shift you can do is when you shift by a purely imaginary amount. So you shift is j omega 0, and then just go back to what we kind of doing in Fourier transform. That is, you do a pure frequency shift, and so s shifted by j omega 0, and RC doesn't change at all, and you see your x get multiplied by extra e to j omega 0t, because you get the extra frequency shift. And so you get this extra exponential, complex exponential vector e to j omega t. Okay, and yeah, yeah, and so even though so in this case the ROC doesn't change, but the point 0 still gets shifted. So your point 0 will shift by a vertical amount on j omega 0. Okay, and yeah, that's what happens when you modulate y. And you can look at this other way around. So you see that when you modulate your signal by complex exponential e to j omega t, then your Laplace transform gets shifted by j omega 0, and the ROC doesn't change, but all the point 0 also gets shifted by j omega 0. Okay, and the next one is time scaling. Once again, we skip the formula derivation, and the formula is more complicated now. Okay, and here we do is instead of x over t, we have x over at. Excuse me. And well, because the time we usually think about is real, so a is a real number. And the formula is a bit complicated. So kind of stretch time by a, then you will squeeze s by 1 way. Okay. Squeeze s by a. So you have multiply by a here, and s divided by a here. That's just as usual. And then you have this extra factor of 1 over absolute value of a. And ROC is getting changed by an interesting amount. So ROC goes from R to A times R. So if A is bigger than 1, then your ROC becomes bigger. A has less than between 0 and 1, your ROC gets compressed. And all A can be also negative. So when A is negative, then your ROC is either stretch or compress and also flip around. So let's see some example. Okay, so we have an example here. So we have a starting ROC here, and we have an example where A is less than 0. Okay, so A is less than 0. So your S this signal, I think your signal got compressed because you multiply by something bigger than 1. Your signal got compressed, and your ROC also got compressed because your ROC got multiplied by some factor less than 1. So signal got compressed, frequency domain signal got compressed, and ROC also got compressed. That's nice. And also, we see that we have another example here. So ROC is negative and also compressed. So the signal is compressed and inverted, and ROC is inverted and compressed. Okay. So here we have this R1 will be less than R2, and we have this AR1 now is. So we have this right side is less than the left side, and now we have the left side is less than the right side, like this. Okay, and you can imagine if you have a less than -1, then this will be stretched, but also left and right flip around. Okay, and as a special case of this, so if you just plug in a equal to -1, then you have x over -t. Laplace transform to big X over -s, with ROC also flip around. Okay. And so this is just like before. You have in the Fourier transform, you have negative sign in your t, then you have a negative sign omega. Then we see that well, not only the imaginary part got inverted, also the real part of S got inverted. So yeah, so this looks like a very symmetric relation. You have -1 on t, and you have -1 on S. Okay, question? And yeah, so ROC will also get inverted, you need to remember that. Okay, we're going, about okay time, going pretty fast, yes. And yeah, so that's time reversal, and then we have the frequency reversal, or conjugation as usual. I guess this is not quite the frequency reversal, but anyway, we have conjugation. So just like before, we have if we conjugate our time domain signal, then our frequency domain signal got conjugated, and also in the Fourier transform we have the omega got inverted, and now it's the S will get conjugated. Okay. So yeah, so I guess this is what it is, and once again we skip the derivation, and ROC is doesn't change. ROC is the same, and yeah. So time domain single conjugated. So small x star will Laplace transform to big X star of small x star. Okay. And then once again, we can think about how this works when x of t is real. X of t is real means that x of t equal to x star of t. That means big X of s equal to big X star of s star. And then we want to use a form that's more useful is you take a star on both sides and using x star of s equal to x of s star. Oh, sorry, we have a typo here. This should be small s. Okay. And yeah, so big S star of s equal to big S of s star. Okay. And okay, and now this thing is useful now because it can tell us a little bit about the point zero structure. Because okay, the derivation is a bit complicated, but let's assume x of t is real, and then we have this thing. And now we think about some, I say that S0 is a point of 0. Okay, so like x of s, so say x of x, so big X of s is unbounded over 0 at s over 0. And that means, okay, so maybe I should write here. Okay. So for example, that's is big S of so what I want to say is 0 or infinity is conjugated to 0 or infinity. So x of s0 equal to 0, then that means x star of s0 is also 0 because the 0 conjugation is 0, and that means big X over S star is 0. S0 star is also 0, and here we can also put infinity here. Okay, and yeah, so if x of S0 is infinity, then x star, then infinity conjugation is still infinity, so x star of S0 is also infinity, and that means that x of s star is also infinity, and that means if you have 0 or infinity at 0 pole at S0, and you will also have 0 or infinity at S0 star. Okay, and yeah, so that means if you have a real, if your x of t is real, then your point 0 structure should be like symmetric along your real axis. So we have our example here. So we see that so these are two previous point 0 structure we draw. So the first one should be this one, and we see here all the point 0 lie on the real axis, and so they are conjugation to their self, so it's okay. So S0 equal to S0 start, and yeah, so yeah, so that satisfies this equation. And we also have this more complicated example where we actually have a complex point 0. Then we see that we have 0 here, then you have a symmetric 0 here because its complex conjugation should also be a 0. And also we have a pole here, and its complex conjugation should also be a pole. And once again, if it's on a real line, then it's okay. Okay? Any questions so far? So yeah, the conjugation property tells us that this is the next property about point 0. Point 0 structure on the S domain. And you can kind of also derive, never mind, yeah. Yeah, so that's for real function. Okay. Okay, so that's a conjugation, and let's go to the next property. It's a convolution property. And convolution property, just like before, it says that convolution in time Laplace transform to multiplication in frequency or S domain. And once again, the ROC, just like linearity, is the intersection between R1 and R2. And by also containing, so it can be bigger. And that's just because, like before, we can have a point zero cancellation. And here we have a very trivial example. So we have x1 is s plus 1 over s plus 2, and x2 is s plus 2 over s plus 1. And we see that you have x1 multiplied by x2. Then your ROC become the entire S-plane, because x1 times x2 is 1, and there is just no poles on this thing, so the ROC should be the entire S-plane. Okay? Question? Okay, and yeah, the next one is differentiation in time. And differentiation in time, just like before, is pretty straightforward. So dx dt Laplace transform to HRS here. So S big S of S. And ROC is also ROC containing R, because this S here is 0 at S equals 0, so you can cancel a pole at S equals 0. And the derivation, we have a very quick derivation here, is from this inverse Laplace transform equation, and we take a differential of tan on both sides, and you see that it's become dx dt, and only c depend on t here is this e to the st, and so you get the HRS here. And also differentiation in x domain, we can also do derivation by doing dds on both sides of this Laplace transform equation. And so dds, this becomes dds, and here you ds, you get h1 minus t here. So you see that you do differentiation of frequency here, or differentiation of s here, and you get h1 minus t factor here. And ROC we can also doesn't change. Okay, and here we see an example. Okay, this is actually useful example. So example used to derive our higher order partial fraction expansion to do inverse Laplace transform. Okay, so so we want to find the Laplace transform of x of t equal to t e to the minus at u of t. So this is actually kind of inverted of what we want to do. But anyway, so we know e to the minus at u of t Laplace transform to 1 over s plus a with the real part of s greater than minus a. This is the first example we see, and we do a lot of things about. We've done a lot with this example, and now we want to use differentiation formula on it. And so because we know HRT factor can be getting from dds, and also multiply both sides by a minus sign. Okay. So HRT factor can be given by you take a differential of s and a h1 minus sign here. And then you do this differentiation, you see that this is 1 over s plus a squared. Okay. And as we said, ROC doesn't change. Okay. And so this is we see that you get a higher order partial fraction if you have this HRT here. Okay. And then we can give an even higher order by just doing more differentiation. Then we see that if we want a third order here, then it becomes t squared over 2. And if it's nth order in general, is t to the n minus 1 over n minus 1 factorial. Okay. And yeah, so now you can do inverse Laplace transform to all of any order partial fraction by just looking at plugging in this formula. I guess you need to do the other one. So this is only the real s plus bigger. These are only the right-sided functions, and there will be a very similar function for the left-sided functions. But for now, let's use this for inverse Laplace transform for right-sided function. Okay, and so now we have this 2s squared plus 5s plus 5 over s plus 1 squared times s plus 2, and with everything right-sided, so real s greater than minus 1. And now we see this as a double pole at s equal to minus 1, and a single pole at s equal to plus 2. And because of this double pole here, when you do partial fraction, we actually have three terms. So second order term of this double pole, and the first order term of this double pole, and the first order term for this single pole here. So something over x plus 1 squared plus something over x plus 1 plus something over plus x plus 2. And if you do the partial fraction expansion correctly, you see the coefficient here should be 2 minus 1, 3. And LC is the right-sided one. So I guess let's do a positive plot here. And 0 we skip, but pole we have. So pole we have a pole is minus 2 and kind of 2 poles, but we don't have a good way to draw double pole. Let's just draw it heavier. Okay. Double pole is minus 1, and RC is the right side of everything. Okay, and RC is the right side of everything. So when we do invert, then we see that the RC. So every one of this partial fraction should be inverted to the right-sided equation. And the right-sided signal, we have this formula here. And so the second order term got inverted to HRT here. And the first order term, as usual, is e to the minus AT with a equal to 1. And this is e to the minus AT with a equal to 2. And also the HR vector 2 minus 1 is 3 here. And times u of t. Question? Okay. And then the next one is integration. So this one is a bit funny because it's very simple. So integration is actually just the straight invert of differentiation. So if you x of tau d tau, so if your function is some x of tau and the integration d tau from minus infinity to t, then its Laplace transform is just 1 over s big X of s. And this is in comparison to the Fourier transform has a extra delta term, but in Laplace transform, because RC is just avoiding this delta term, so we only have this 1 over s term here. Okay, and as I said, so the RC containing the intersection between R, so R is RC of x of s, and the real part of s greater than 0, that's the RC of this 1 over s. Okay. So kind of avoid the Fourier transform line here, we avoid the delta function at s equal to 0. Okay. And yeah, by saying that's not in RC. And so our in the integration formula for Laplace transform is actually just the invert of the differentiation formula here. So differentiation formula get the HRS, integration formula get the HR 1 over s. Okay, and yeah, and we do a derivation by kind of by using the convolution formula. And so we say that this integration is convolution between x of t and the unit step function u of t. And then we say the unit step function is this exponential decay function that we like most about. Okay, is this unit step function is just e to the minus at u of t with a equal to 0. So we say that u of t Laplace transform to 1 over s with the real part of s greater than 0. Okay, and yeah, so u of t Laplace transform to 1 over s with the real part of s equal to 0, greater than 0. And by the convolution formula, we have the convolution on the time domain, then we have multiplication on the frequency domain. So it just is 1 over s times the Laplace transform of x of t, that's big X of s. And with the and yeah, and with the RC being the like we said, the intersection of the RC and before and the RC of real part of s greater than 0. And there might be some positive cancellation to get your RC bigger. Oh, question.
那个 R 和那个 R 那个 S 的 real part 大于那个 R 是什么意思？
这个 R 吗？这个 R 是这个 x of t 的 RC， 所以我们没有写，但是就是跟以前一样，我们是说 x of t Laplace transform 到大 X of s with ROC 等于某个 R 这样子。 we have enough time. And finally, we have a last property that we never seen in Fourier transform, that they are the initial and the final value theorems. Those are very interesting things. Anyway, I think the picture are very nice. So let's try to let's say this is 0. Okay, and yeah, it says that if your signal is kind of the initial rate signal, so we have the interesting property says that if a signal starts from say 0, so x of t is 0 for t less than 0. So if a signal starts at t0 and it's nice at t equals 0, so there is no impulse or weird things, then the Laplace transform can tell you this starting point of x of t at 0 very nicely, very easy. So you can tell you this x of 0 plus, so how where does the x of t start when t equals 0? Okay, and and you can just calculate it from this initial value theorem. It says the x of 0 plus, so this point here equal to I guess I don't really know this. Okay, so I can use this picture here, easy. So I should maybe just use it here. So t equals 0 here, and so this point is our x of 0 plus. Okay, so I need to draw two things here. So that's b. Okay, and so this point is our x of 0 plus. Okay, so you can find this value by having your Laplace transform and multiply by s and take a limit of s go to infinity. So if this thing converges to some finite value, then you will have some finite value x of 0 plus. And then also we can think about okay. And also we have this initial value theorem, and then if we have the same thing, same condition, x of t equals 0 for t less than 0, and and then we can find the final value. So if x of t go to some approaching to some limit here, and the final value can be calculated by a very similar formula. So still s times x of s, and now you take s equal to 0. Okay. And yeah, so the derivation is in homework. It's some problems you can do. Okay. And but okay, so this those two theorems will be useful when you take a more advanced course and analyze your system. But for now, we just say they are useful for doing something easy. That is, you can use it to check whether your Laplace transform is quite correct. Okay. So for example, we have this example 9.4. We have this where weird function x of t equal to e to the minus 2t u of t e to the minus t cosine 3t u of t, and obviously it satisfies the condition over here. So for t less than 0, our x of t just got cut off by both u of t, and it's just both 0. And they want to see what's the initial value of this, and the initial value of this you can check very easily. So you take a t equal to 0, and on the plus side, so this u of t equal to 1, and the other thing when t equals 0, this e to the minus 2t is just 1, and this is also 1, and the cosine 0 equals to 1, so this is 1, and the t equal to 0 plus, this is 1 plus 1 equal to 2 here. And also we had the Laplace transform has like this form, so it's a rational formula, and so it's this rational formula, and you with extra s here, then you have this 2s cubed plus 5s etc. And then you take this, when s go to infinity, then you only look at the highest order term, right? So here you only need to look at the highest order term, and you see the highest order term match, they are both s cubed. So when s goes to infinity, you only look at this, and the s cube cancel with s cube, so you're left with 2. So you see that this 2 is consistent with the initial value theorem. And I guess we can also look at the final value theorem here. Okay, so final value says that when t goes to infinity, this thing goes, both of them go to 0 because of those exponential decay. And you can also see this thing when x goes to 0, then you only need to look at the lowest order term here, right? So the final value, you look at the lowest order term, then you see the 12s over 20, and s goes to 0, this goes to 0, this is still 20, so final value is 0 as we see here. Okay, and we have 5 more minutes, but I think it's good time to stop. But I guess we can show this a little bit. So we have the table of property. Okay, so this is actually a quite short table here. So we have the table of property for our Laplace transform. And let's do a little bit. Okay, and so we have a signal. So signal x, small x goes to big X, and with RC R, big R, and small x1 goes to big X1 with RC R1, small x2 goes to big X2 with RC R2. And so here, I think all the property we talk about today. So linearity a small x1 plus b x small x2 go to a x1, a big x1 plus b big x2. And the RC is at least the intersection between R1 and R2. And then we do time shift. T goes to t minus t0, then you get h r e to the minus st0, and RC doesn't change. And then shifting S domain, so S go to S minus S0, then then your R shift to R plus S R plus S0 basically. So here it didn't say, so that's right here. Oh, it's really small. Here this thing should be R plus I guess the real part of S0. Okay, and yeah. Okay, and let's go back to magnifier. And yeah, this is shifting in S domain, and then in time domain you get h r e to S0t. And then we have time scaling, t goes to at, then you get on the frequency domain, you 1 over absolute value of a, big X of S over a, and ROC will be scaled. And here we also didn't write, so ROC become AR, as we know today. ROC become AR. Okay, and then the next one. Conjugation, x got conjugated, then big X got conjugated, and the S also got conjugated, and RC doesn't change. Then convolution on the time domain got the multiplication on frequency domain. And the RC is once again at least the intersection between R1 and R2. And the differentiation in time domain got the HRS in S domain, and the RC is at least the same RC. And the differentiation in the S domain, then you get HR minus T on the time domain. RC doesn't change. And finally, you have integration. No, not finally. So, and also you have integration in time domain. Then you just get 1 over S in the frequency domain. This is a bit different from Fourier transform because you don't get a delta function. You just say your RC is your original RC. Intersection with the ROC of 1 over ROC of unit step function, that's real part of S greater than 0. And finally, you have those two interesting initial and final value theorem. Says that you need to satisfy those conditions. So x of t equals 0 for t less than 0, and it has no weird singularity at t equals 0. Then the initial value will be limit s go to infinity, s times big X of s, and the final value will be equal to still s times big X of s, taking a limit of s equal to 0. Okay, any questions? If not, I think that will be today, and we'll see you on Friday, and let's see how much we can. Yeah, we should be finishing this chapter soon. Okay. Yeah. So see you.